Jai Hind, good morning and welcome to this lecture number 8. I am Professor Devendra Singh taking the course on machine design, and in the last lecture we have discussed about the various modes of failure against design against static load as well as the factor of safety we have discussed, and we have moved to the introduction of theories of failure. And we have discussed in the last lecture why theory of failure is needed, because in case of the uniaxial loading, it is very easy to compare the induced stress with the material property, that is the strength of material or permissible stress, and we can formulate the design equation by comparing the induced stress and the allowable stress. But in case of the complex state of stress, जहाँ हमारी कॉम्प्लेक्स स्ट्रेसेस आती हैं दो डायरेक्शन में या तीन डायरेक्शन में और कॉम्बिनेशन ऑफ नॉर्मल स्ट्रेस एंड शियर स्ट्रेसेस इन रियल टाइम प्रॉब्लम में आती हैं, देन इट इज़ वेरी डिफ़िकल्ट टू डिसाइड कि व्हाट magnitude of induced stress should be compared with the material property to formulate the design equation, determine the dimension of the component under the loading condition or for the application what is desired to perform by the design component or design system. So, this particular lecture will be dedicated to the theories of failure. We will try to understand कि theories of failure क्या होती हैं, कितने तरीके की theories of failure हैं, statements, equations क्या हैं, and graphical representation क्या है, कौन सी theory हम किस मटेरियल के लिए और किस कंडीशन में इस्तेमाल कर सकते हैं कि नहीं कर सकते हैं, ये हमें मालूम होना चाहिए. अगर हम सही थ्योरी ऑफ फेलियर किसी एक पर्टिकुलर मटेरियल के लिए नहीं इस्तेमाल कर पाते हैं, नहीं खोज पाते हैं कौन सी थ्योरी ऑफ फेलियर वहाँ हमें इस्तेमाल करनी चाहिए, उस केस में जो रिजल्ट्स हैं वो एरनियस हैं. और आई हैव डिस्कस सेवरल टाइम्स कि एरनियस डिज़ाइन केवल मॉनेटरी लॉस नहीं, it can cause more than that. So, it is very essential to select the appropriate theory of failure for a particular design as per the requirement. So, the content of this lecture includes first that we have covered in the last lecture, that is modes of failure under static load we have discussed. There were three modes of failure. Factor of safety, this is some simple a number. I have discussed this in the last lecture, and the optimum factor of safety should be included in the design to make your design successful and safe. Then introduction theory of failure we will discuss. We start today in this lecture. Then we will discuss maximum principal stress theory, maximum principal strain theory, maximum shear stress theory. So, what is theories of failure? As I have already told you that in the uniaxial state of stress, it is very simple to formulate the design equation, but in case of the complex state of stress, we need to find the induced stress which should be compared with the material property or allowable stress to make the design equation. So, to deal the complex state of stress, we had to form or we had to think something, and this is come in the form of the theories of failure. So, this is there are 5 theories of failure primarily. These are the maximum principal normal stress theory, or other name is the Rankine's theory, जिसने इसे दिया उसके नाम पे. Maximum strain theory, St. Bernard's theory, maximum shear stress theory, that is the Tresca and Guest theory. Then maximum total strain energy theory, that is Higgs theory, and maximum distortion energy theory, von Mises and Hanke theory. In fact, maximum strain theory and maximum total strain energy theory are not in use. These two theories of failure have already been obsolete, and maximum principal stress theory, maximum shear stress theory, maximum distortion energy theory, these theory of failures are in use for the design purpose, but for academic purpose we will discuss all these 5 theories of failure during our discussion. So, first is the maximum principal stress theory. So, as per this, so this theory primarily uh, यूजफुल और इस थ्योरी ऑफ फेलियर को हम यूज़ करते हैं primarily for the brittle materials. So, as a statement of any theory of failure, maximum principle or normal stress theory means कि अगर किसी भी लोडिंग कंडीशन में रियल टाइम स्टेट में मैक्सिमम प्रिंसिपल स्ट्रेस जो इंड्यूस हो रही है उस कंपोनेंट में, वो परमिसिबल स्ट्रेस से के बराबर या उससे एक्सीड होने की स्थिति में आ जाए, सो वी से कि अवर डिज़ाइन इज गोइंग टू बी फेल. फॉर सक्सेसफुल डिज़ाइन द प्रिंसिपल स्ट्रेसेस शुड बी less than or equal to the permissible stress or the yield point of stress. Yield point of stress or yield point in tension we consider as a designer as the failure stress. So, we can say if the maximum principal stress induced in the material in the real time application reaches to the tensile stress in the simple uniaxial tensile stress, then we say our design is going to be fail. So, it should be lesser than that. So, the statement you can see, this is the material is going to fail as soon as any of the principal stress reaches to the value equal to or greater than the yield point in tension. Suppose there are three principal stresses sigma 1, sigma 2, sigma 3. So, ये condition हो सकती है कि sigma 1 is greater than sigma 2 is greater than sigma 3. So, if sigma 1 is the largest, if I say sigma 3 is the smallest, if sigma 3 is less than or equal to sigma 3 is equal to the SYT, then it means our design is going to be fail. We have to change the design, we have to change the material, we have to design the dimension accordingly to make our design successful. And if sigma 1, which is the largest principal stress, अगर ये sigma 1 less than or SYT, SYT I consider as the yield point in tension, and I have told you that this maximum normal stress theory is applicable for the brittle materials. So, in case of the brittle material, we do not get this SYT, then this you will change by UT, means ultimate tensile stress. So, if sigma 1 is less than or equal to, it means our design will be a successful condition, and if sigma 3 is greater than or equal to SUT or SYT, uh, in case of the brittle material SYT, in case of the ductile material SYT, then it is a failure condition. So, this is the philosophy to formulate the design equation. Sigma 1, sigma 2, sigma 3 are the induced principal stresses, and if some factor of safety we need to use, then these failure stresses should be divided by factor of safety. So, this is the philosophy. So, these are this I have already discussed here. Sigma 1, sigma 2 and sigma 3 be the three mutually perpendicular principal stresses, and SYT is the yield point in tension. If I am dealing with the brittle material, if it is if I am dealing with the ductile material, but if material is brittle, then I will use SUT, ultimate point in tension. Then sigma 1 is less than or equal to SYT, sigma 2 is less than or equal to SYT, sigma 3 is less than or equal to SYT. These are the successful condition. तीनों की तीनों इसमें इससे कम हो सक्सेसफुल कंडीशन है, और अगर सबसे छोटी वाली इंड्यूस स्ट्रेस हमारी SYT से कम है, तो हम ये डिसाइड कर पाते हैं नहीं कर पाते हैं, यह हमें सोचने की आवश्यकता है. बहुत ध्यान से इस चीज़ को हमें देखना चाहिए कि अगर सक्सेसफुल कंडीशन, तो हम कहेंगे कि जो हमारी लार्जेस्ट प्रिंसिपल स्ट्रेस है, अगर वो हमारे फेलियर स्ट्रेस से कम है, तो बाकी दो नेचुरली कम होंगी, बिकॉज सिग्मा 2 सिग्मा 3 सिग्मा 1 से कम है, तो दिस इज कंसिडर्ड एज अ successful condition. And if you want to incorporate some factor of safety in your design, then these SYT failure stresses you have to divide by factor of safety, and the design equations will become this sigma 1 is less than equal to s y t. So, these are the safe condition or successful condition when factor of safety is equals to 1, and if there is some factor of safety you want to use, then these are the design equations. We need to find out sigma 1, sigma 2, sigma 3 as per the applied as per the given state of stress, and we will have this design equation s y t s or s u t as per the material. These are the known quantities. So, this is the philosophy. So, this is the safe condition, this is the safe condition, uh, this is the safe condition with desired factor of safety. So, as per principal stress theory or Rankine's theory. Now, the graphical representation. So, sigma 1, sigma 2, sigma 3 should be less than or equal to s y t, and plus sign means in the state tensile nature of loading, and negative nature of loading is compressive. So, here this is assumed that the s y t, this is assumed that the s y t in tensile must be equal to s u c, then s y c. This is in compression. This is an assumption. I have assumed कि material ऐसा है जिसका yield point in tension या yield point in compression same है. So, I will write in place of s y c minus s y t. So, this is there. So, to draw safe condition for factor of safety 1, if the largest principal stress is less than or equal to s y t, the material remains safe. I have discussed in the last slide. So, first we draw the planar stresses to draw on the plane. So, this is sigma 1 sigma 2 plane. So, same convention we are using here as coordinate geometry. On the right hand side of the origin, the positive sign, that is tensile, upside is the tensile, and left side and downward is the compressive or the negative. So, O is the origin here, and then we mark s y t on the right hand side. So, sigma 1 is equals to s y t. So, this is the line sigma 1 is equals to s y t. This is a line which is having a constant abscissa value, sigma 1 value. Then s y c, I will replace it with minus s y t, or you can write s y c. The s y c and s y t are equal in magnitude, may be the different. For if the material is different, then this is the line. So, sigma 1 is less than or equal to s y t. So, this is our safe zone this side, and sigma 1 is less than equal to s y c. This is the safe zone. Similarly, for positive sigma 2 s y t. So, the line where ordinate is constant, this is line parallel to the abscissa s y t, and then if this is in compression, this is the another line. So, this is the safe zone, this is completely, this is the safe zone, where if your loading condition lie in between inside this rectangle or the square, then your design is successful with factor of safety is equals to 1. If you want to design something with a desired factor of safety, then you have to decide, you have to divide the failure stress by f s by factor of safety, and you will get the smaller rectangle. So, a smaller square for the safe design. So, this is colored zone is the safe zone. Now, this is Rankine's theory with desired factor of safety. Here, this is the design equation where we want to incorporate some factor of safety. So, same procedure to plot safe condition, and If the largest principal stress is less than or equal to SYT upon FOS, then the material remains same in the loading condition, and this is sigma 1 sigma 2 plane, and again find out the points. This is origin, then SYT is there, this is the earlier line drawn in the last slide, this is SYT for sigma 2, this is SYC for minus sigma 2. This is the rectangle or square. If SYT is equals to SYC, then it is square, otherwise this is this is rectangle. So, this is the safe zone with factor of safety 1. Now, the failure stress divided by factor of safety. So, this is the new point SYT upon FOS. So, this is the line and sigma 1 sigma 2 plane. Similarly, on the left hand side SYC upon factor of safety, this is another line, and sigma 2 SYT upon factor of safety, and similarly this is the safe zone. This colored zone is the safe zone with factor of safety according to the maximum principal stress theory, Rankine's theory, and this the white zone here outside this, but inside the larger one, larger rectangle or square, that is called, this is the danger zone or unsafe zone for this factor of safety. So, this is, that is why I shown this area with the red color. So, this is unsafe zone, and with green color this is the safe zone as per the theories of, as per the Rankine's theory. Now, the next theory is the maximum strain theory or Saint-Venant's theory. Again the statement you can formulate as we have written the statement for the maximum principal stress theory or Rankine's theory कि अगर लोडिंग कंडीशन में जो इंड्यूस स्ट्रेसेस हैं वो मटेरियल की प्रॉपर्टी, जो हमने मटेरियल की फेलियर स्ट्रेस है उससे कम रहती हैं तो सेफ है, अगर उसके बराबर है उससे ज़्यादा हो जाए तो फेलियर है. स्टेटमेंट था कि इफ द इंड्यूस्ड stresses or induced stress of any principal stress reaches to the value equal to or greater than the yield point in tension under the simple uniaxial tensile test, then the material is said to be failure. Here the property which we will try to compare or which we will consider the critical property is the strain. So, if I write in place of the stress a strain or principal strain or the normal strain, then this the statement will become for the maximum strain theory or the Saint-Venant's theory. And strain is related to stress because we, as far as the strength design is concerned, we want to we want to keep our design within the elastic limit, or if it is possible within the proportionality limit. So, that Hooke's law should be valid. So, strain is directly proportional to stress. So, E is constant, that is material property. So, अगर stress हमारी कम है तो स्ट्रेन भी कम होनी चाहिए, ये चीज़ें हमारा दिमाग में आती हैं. अब देखेंगे कि क्या डिफरेंस है. सो फर्स्ट वी see the statement, the material is going to fail as soon as any of the maximum normal strains in any direction reach a value equal to or greater than the strain at elastic point. Here I write this elastic point y because I relate, when I convert the statement of a strain or the expression for strain in the strain, then I will use the Hooke's law, and tension during the uniaxial tensile test. This is the statement. So, if epsilon 1, epsilon 2, epsilon 3, if I denote the strain by epsilon, and epsilon 1, epsilon 2, epsilon 3 are the strains in the direction or caused by the stresses sigma 1, sigma 2, sigma 3, these are the principal stresses. So, what you can write these are this is suppose the loading condition in which sigma 1, sigma 2, sigma 3 these are the three mutual perpendicular principal stresses. Now, if epsilon 1, epsilon 2, epsilon 3 be the three mutually perpendicular principal strains and epsilon y t is the strain at the yield point in the material when it is subjected to the tensile test. So, the strain appears at the yield point जहाँ yielding start होती है वहाँ पे जो strain आती है उसकी वैल्यू एप्सिलॉन बाई टी है और इस एप्सिलॉन बाई टी को अगर हम फैक्टर ऑफ सेफ्टी से डिवाइड कर देंगे तो परमिसिबल strain या लाबल strain आ जाएगी. So, if we consider these three dimension cases for the stresses of same nature tensile और compressive, ये हमें ध्यान देना कि सेम नेचर के हैं या डिफरेंट नेचर के हैं. स्ट्रेन की अगर मैं बात करूं यहाँ पे तो अगर ये सेम नेचर के हैं सपोज फॉर एग्जांपल मैं यूनिएक्सियल दिस इज ए ब्लॉक इसको मैंने इधर खींचा तो इसका डिफरेंस क्या आएगा. इसका डिफरेंस आएगा कि ये इधर को बढ़ेगा, ये इधर को बढ़ेगा और दूसरी तरफ ये घटेगा. ये डायरेक्शन इस डायरेक्शन को हम बोलेंगे लॉन्गिट्यूडनल डायरेक्शन जिधर को आपने फोर्स लगाया और इसके डायरेक्शन के परपेंडिकुलर डायरेक्शन बोली जाती है लेटरल डायरेक्शन. सो लेटरल डायरेक्शन में द डायमेंशन विल रिड्यूस. अब इसके अपोजिट हमने अगर इसको लगाते हैं कि एक डायरेक्शन में यहाँ भी आप इसे कम कीजिए तो फिर नॉर्मल इसमें आएगा. तो अगर हम सिग्मा 1 देखें लेटरल डायरेक्शन में स्ट्रेन की बात करें तो इफेक्ट अलग अलग है. सिग्मा 1 सिग्मा 2 तो एक डायरेक्शन में इफेक्ट किया तो दूसरी डायरेक्शन में जो स्ट्रेस है वो उसे सपोर्ट करेगी कि सब्ट्रैक्ट करेगी. तो प्राइमरली वी शुड थिंक इन दैट डायरेक्शन कि किस डायरेक्शन में हम कंसीडर कर रहे हैं. तो उसके परपेंडिकुलर डायरेक्शन की जितनी भी स्ट्रेसेस हैं अगर वो अपोजिट नेचर हैं तो वो स्ट्रेन को बढ़ाएंगी. अगर यहाँ से मैं दबाना शुरू करूँगा तो इसे आगे बढ़ाएगा. ये जब हम स्ट्रेस का इफेक्ट देखते हैं तो उसे एनालाइज करने के लिए सबसे अच्छा तरीका है कि जिस स्ट्रेस का आपको इफेक्ट देखना है पहले उस डायरेक्शन में देखें और जब बाकी स्ट्रेसेस की बात करनी है तो पहले वाले को समझें कि वो वहाँ नहीं है तो केवल वो दूसरा जिस पे आप कंसंट्रेट कर रहे हैं वो इफेक्ट क्या देता है वो पहले वाले में ऐड करेगा कि सब्ट्रैक्ट करेगा. तो यू कैन डिसाइड द साइन whether it is additive or subtractive easily. So, on that basis if these are the same tensile or compressive अगर ये same nature की होंगी तो हमेशा माइनस साइन एक्सप्रेशन आने वाला है. You can remember if they are opposite in nature एक टेंसाइल हो दूसरी कंप्रेसिव हो तो वो एक दूसरे को ऐड करेंगी और इसलिए एडिशन में आएगा. तो हम नेट एप्सिलॉन 1 की बात करें और हमने टेंसाइल ले रखा है तो सिग्मा 1 अपॉन ई सिग्मा 1 की वजह से सिग्मा 1 की डायरेक्शन में कितनी स्ट्रेन है सिग्मा 1 अपॉन ई. और अगर सिग्मा 2 सिग्मा 3 ये और ये भी सेम नेचर की है टेंसाइल हैं तो न्यू इज पॉइसन रेशो. न्यू इज द पॉइसन रेशो. सबको मालूम है व्हाट इज पॉइसन रेशो. पॉइसन रेशो इज लेटरल अपॉन लॉन्गिट्यूडिनल स्ट्रेन. सो न्यू टाइम्स सिग्मा 2 अपॉन ई. सिग्मा 2 अपॉन ई जो लेटरल डायरेक्शन में कंट्रीब्यूट करेगा तो इसे घटाने की कोशिश करेगा. ये इसे खींचेगा तो वापस यहाँ पे अगर हमने ये सिग्मा 1 माना ये सिग्मा 1 माना और फिर सिग्मा 2 को देखा सिग्मा 1 यहाँ तक लेके आया इसे सपोज यहाँ तक एक्सटेंड कर दिया. सिग्मा 2 को मैंने एब्सेंट माना था. अब मैंने सिग्मा 1 को एब्सेंट माना और सिग्मा 2 को लगाया तो सिग्मा 2 इसे ऊपर लेके आ रहा है. अब कितना इफेक्ट दोनों एक साथ लगाएं तो कितना इफेक्ट. सो उसके लिए एक प्रॉपर्टी है मटेरियल की दैट इज पॉइसन रेशो. यू हैव लर्नड इन योर strength of material. So, sigma 1 upon E minus nu sigma 2 upon E plus similarly you can consider the effect of sigma 3 that is also in tensile in nature. So, the strain is caused in the direction of sigma 3 is sigma 3 upon E, and in the perpendicular direction it will contribute with negative sign nu. So, this is the net stress epsilon 1 in the direction of sigma 1 under the effect of sigma 1, sigma 2, sigma 3. This you have already learnt in your strength of material. Similarly, you can write for epsilon 2 and epsilon 3. Similarly, you can analyze these easily. These are your expression. So, first term is always whatever direction. So, epsilon 1 sigma 1 upon E and remaining 2 in some way negative minus nu, epsilon 2 sigma 2 upon E is the first term, 3 and 1 in sum in the bracket multiplied by minus nu add kar दें और sigma 3 upon E. These are the net strain in the direction of sigma 1, sigma 2, sigma 3. So, now for two dimensional cases planar stresses, we are moving towards the graphical representation. So, we will take let sigma 3 is equals to 0. So, if you see sigma 3 is equals to 0 here. So, what is epsilon 1, epsilon 2 and epsilon 3. So, put sigma 3 is equals to 0 in this expression, what you will get sigma 3 I made equal to 0, here sigma 3 is equals to 0. In fact, in the direction of 3 stress is 0. So, as per the Hooke's law epsilon 3 is equals to also 0. So, the equations which are available for us for our interest, this is epsilon is sigma is equals to sigma 1 upon E minus nu sigma 2 upon E, epsilon 2 is equals to sigma 2 upon E minus nu sigma 1 upon E. These two equations remains for us. This is 1, if sigma 1 is greater than sigma 2, then sigma 1 upon minus nu sigma 2 upon E epsilon 1 direction में, then epsilon 2 sigma 2 upon E minus nu sigma 1 upon E, if sigma 2 is greater than sigma 1, that condition you can show. Now, factor of safety. So, epsilon max must be less than or equal to epsilon E t or epsilon y t. E t is the elastic limit that I have already mentioned why I am using this elastic limit. This should be sigma 1 upon E minus nu sigma 2 upon E should be less than or equal to sigma t upon E is equals to SCT upon E, and if you take this sigma 1 minus sigma nu sigma 2 is less than this. So, these are the expressions sigma 1 sigma 2 compressive. So, these are our theory of failure in terms of the stresses maximum strain theory. Next theory of failure I will start in the next lecture. Thank you very much.